Okay, then let us begin. See, yesterday we were talking about Werner's postulate, if you can recall. Okay, I'll just have a quick revision of it. So in Werner's postulate, what I told you is, from the experiment, we got to know that there are two types of valences, okay, that is linkages. We got to know there are two types of linkages, also called as valences, okay. So he named them as valences or linkage. It's just a bonding, okay, which we are talking about. So there were two types of valences which we saw. One is primary and the other one is secondary. So I'm writing 1 degree and second degree. So this 1 degree indicates it's primary and 2 degree indicates it is secondary. Okay, so two types of valences, primary and secondary. So this will be the first postulate, okay. So it's very simple to actually remember. And it's important also. See, this Werner postulate, from your exam point of view, it is important because they ask you to write the postulate. But from the practical point of view, from our now current situation wise, it has been outdated. So we don't accept this particular theory. We don't learn about this theory, okay. In practical cases I'm talking about, but from your exam point of view, they have been asking these questions many times. So from that point you are learning, so learn this correctly, and it's like important also, and it's easy as well to remember. So I said primary and then secondary. This primary, if you have seen, I said it can be existing inside as well as outside. This is like I am giving you the hint part, okay. Don't write inside and outside like that. Just I gave you the hint over here, okay. Like for example, if you have a metal, you know metal usually will be found inside the coordination sphere. Okay, so when we write that coordination entity, usually metal will be found inside, and then attached to that you will find there is a ligand. Okay, then outside that you find the counter ion, correct? No, that I will label as X. Okay, most of the time this X which is there, they will be primary valency. Okay, but then this primary valencies can be found inside also. Okay, it need not be that, because sometimes this negative ions which are present, they will be inside, which will be satisfying the oxidation state of the metal. Okay, whatever charge the metal carries, no, that will be satisfied even if they are present inside. So do remember that primary valencies can be present outside, they can be even present inside. Okay, this is only for you to get the hint, because sometimes students, they get confused about the primary valences. They think only the one which are present outside and the one which reacts to the solution which is added and precipitate out, only they are the primary valencies. No, it is not that case. Primary valencies are the one which satisfies the charge of the metal. So they can be present, I said, inside. They can even be present outside the complex. Okay, but secondary valencies are there. No, they will be always present inside. So there is no second orders. So they will be always got inside. So whatever you are able to see attached with the metal, that will be the secondary valencies. Okay, and that will be equal to the coordination number. Okay, so secondary valencies will be always equal to, they will be always equal to coordination number. Okay, the number of ligands which they are attached with. Like for example, in this case, CO, NH3, 6, 5 as an example, and then Cl3. Okay, so in this case you can see the cobalt metal is attached with 6 ammonia ligand. Okay, so then in this case the coordination number will be 6. So that itself is a secondary valency. But in the primary valencies, remember, that will be equal to the oxidation state of the metal. That will be equal to oxidation state of the primary valencies are always equal to oxidation state of the metal. So in this case, cobalt NH3 6Cl3, which I have taken here, can you tell me what is the oxidation state of the cobalt here? Students, you know now how to calculate the oxidation state of the metal. Can you calculate and tell me what is the oxidation state over here, everyone? Yes, very good. Yes, 3, everyone agrees, no? 3 is the oxidation state. Very good. So plus 3 will be the oxidation state of that metal. So in this case, it is being found outside. Okay, that primary valencies are found outside, and that satisfies the charge of the metal here. Okay, so plus 3 is the oxidation state. For this example, I have taken here. Okay. And then what I told you, one more point is that the secondary valencies are non-ionizable. Okay, secondary valencies, they don't get ionized into the solution. So they are non-ionizable. They are non-ionizable. Okay, means this whole entity remains as the entity itself. They don't break down into the ions. Like for example, if you take this particular complex which I have written here, okay, in this case, you know there are two entities. One is CO and the other one is 3 chloride ions. 3Cl minus, because you have Cl3 here, that means 3 chloride ions have combined with this particular complex. So this complex, when you dissolve in the water, they will remain as it is. They will remain as this whole ion. So they are non-ionizable in nature. Whereas it is for secondary valencies, okay, I have written it here, sorry. It should be coming for secondary valencies, okay. So secondary valencies are non-ionizable in nature. Okay, so these are non-ionizable in the solution. Whereas primary valencies are there, no? Primary valencies, that is, you can see here, they are ionizable. Okay, most of the time the primary valencies will be ionizable. Unless they are acting as a secondary valency also, then they don't get ionized. Okay, but if they are present outside, then they will be ionizable in nature. Okay, so that is the primary valencies characteristic. And then the next point is the secondary valencies will give you the definite geometry. Okay, they tell you about the spatial arrangement and they give you the geometry. So secondary valencies will decide the complex, because here you can see 6 ligands are attached. So 6 ligands, they will not cluster themselves just like that. Okay, they will arrange themselves in a definite order. Okay, in a polyhedron, they will arrange themselves in a definite order. So they give you the geometry of it. Okay, whereas this one doesn't give any geometry. Okay, so these are non-directional. These are non-directional in nature, whereas the secondary valencies are directional in nature. So this you can keep in your mind. And then one more point what you have is the secondary valencies which are there, they can be satisfied either by the neutral molecules or they can be satisfied by the negative ions. Okay, they can be satisfied by either the neutral molecules or it can be satisfied by negative ions. But primary valencies are always satisfied. Okay. No, isomerism part you don't have, okay, this time to study. They have removed from the syllabus. Isomerism we don't have. Otherwise, we had the whole part of it, which was important topic also. But this time we don't have. The structural as well as stereoisomerism part is not there for your exam, okay. So whatever I've done till now, no, till the Werner's postulate, what I'm doing from till here, it's very, very important, okay. So focus more on this part, whatever I've done till now. So questions will be asked based on this concept only, which I have covered, okay. I hope students it is clear for everyone. I hope you are able to understand this Werner's postulate. Now I'll give you a few examples. You try to answer me what are the primary and the secondary valency. Before that, I will take few examples how to write, like how we were writing the structure of this, how we were representing the primary and the secondary valencies, okay. See, I'll take one example now to represent primary and the secondary valencies. I'll take that same example which I took no that time, that is CO H3 Cl3. Okay. So in this case, what we do is we write the cobalt in the center. Okay, so I'll write the cobalt in the center and then it is surrounded by 6 ammonia ligand. So those 6 ammonia ligands you draw with a definite geometry. You know, if it is 6 ligand, then what geometry they should have is octahedral, correct? No? So we will draw the octahedral geometry for it. So I will write here NH3 minus okay. Okay. So this is how the geometry will come. Okay. So secondary valencies we represent with the solid line. If it is secondary valency, we represent with the solid line. Okay, like this. And if they are primary valencies, we dash. This is only for your understanding. It won't be coming, but they will ask you how to find out the primary and the secondary valency. Now, the primary valency, what we do is they are non-directional, so you can draw it anywhere just to satisfy the charge of the cobalt. Okay, so here what we are going to do is I will just write the dotted line. Okay, so one dotted line, one chloride ion, and then one more dotted line for one Cl. Okay, one more dotted line I'll just draw. They will be just present as a coordination sphere. Okay, so this is how the primary valencies are satisfied. I hope you are able to get this part. Okay, now I'll take one more example. You have to tell me what is a primary and what is a secondary valency. Okay, see here, CO NH3 4 Cl2 Cl. Okay, now tell me what is the primary and what is the secondary valencies. I want everyone to answer. Tell me what is the primary and what is the secondary valency. Primary and secondary valency both. Okay. Yes, very good. That is correct. Secondary valency is correct. Primary valency. Primary valency. Yes. Primary valency, I told you it is equal to the oxidation state. Yeah, 3 is the correct answer for primary valency. Okay, 3 is the correct answer. And 6 is the correct answer for secondary valencies. Okay, good. Few answers I've got. But check out now why it is 6 and 3. See, what did I tell you? Secondary valencies are the one which are directly attached to the metal. So, cobalt is attached with 4 ammonia ligand and 2 chloride ligand. So, secondary valency in this case will be 6. That is correct. Okay. How will be the primary valency? Primary valency, what did I tell you? Primary valencies are equal to the oxidation state of the metal, students. So, your cobalt, oxidation state, you can find out, no? How much will be the oxidation state of cobalt here? Ammonia, anyways, it is 0. 2 chloride ion is inside and 1 chloride ion is outside. Okay, so altogether it is 3, no? So, say primary valency is over here, it is 3. Now, you may be getting confused with that. Secondary valencies and primary valencies of 2 chloride is coming together with the cobalt. Okay, that can happen. That is fine. Okay, that negative ions can satisfy the secondary valency also and it can satisfy the primary valency also. Okay, so that is how it is. So we say, no, it is equal to this. So I told you it can be present inside, it can be present outside. But then you have to see that they are equal to the oxidation state. Okay, they are equal to the oxidation state. So how to draw this particular complex now? How it is being drawn is, see here, cobalt we take inside, okay, 2 chloride ion and 4 ammonia ligands are there. So I will draw that ammonia ligand. I will just draw ammonia here. Simply I have drawn here and then chloride. So I'm just putting right opposite side. You can draw on that also. I have just randomly arranged them. Okay, seeing the total 6 molecules are attached to the cobalt. So I have drawn 6 over here. Okay, now coming to the primary valency. Okay, so secondary valency I wrote here. Now here 1 chloride ion is there, which is present outside. Okay, and primary valency altogether is 3. So means 1 chloride ion is randomly attached like this. Okay, with a dash line. And the 2 chloride ion which is satisfying the cobalt ion, they are showing the secondary valencies as well as they are showing the primary valency. If that is the case, what we do is, one solid line we have written, no, then we write one dashed line also. Okay, so here one dash line is written which indicates that it is having a primary valency also and it is showing the secondary valencies as well. Here also you see, I will put one more dash line. Okay, so I hope now at least you are clear with the primary and the secondary valencies. Did you all get? Or should I give one more example? Here this chloride ion satisfies the primary as well as the secondary valencies. Okay. Okay, I'll give one more example. Yes. Now you should tell me like which is the primary and the secondary valencies and how many dotted line and how many solid lines I should be using. I'll give you one more example. Yes, tell me for this. Now you should answer. I will not answer anything. I want you people to answer. You tell me what is a primary valency and tell me what is a secondary valency. I will give you 1 minute. I want most of them to answer. What is the primary valency and the secondary valency? Yes, few answers I've got. Very good. It's correct. Next, others. Yes, very good. So primary valency is 3 and secondary valency is also 3. I hope you are able to get now. Secondary valencies which are directly linked to the cobalt. Okay. So the link to the cobalt, you can see there are 3 ammonia ligands and 3 chloride ligands. So I can write here secondary valency is 6. Okay. You can find the primary valency. Suppose if you are finding difficult to write down the primary valency, you calculate then. See, cobalt is X. Ammonia ligand don't carry any charge. So I will write here 0. Okay. Chloride ion, you know that they carry -1 charge and such a chlorine we have, that is 3. Here in this complex, the number of chloride ion we have is 3. So I should write -3. And the complex is not carrying any charge. So I should write equal to 0. Correct? No. So X is equal to how much? +3. So that means the oxidation state of the cobalt over here is +3, which is satisfied by the chloride ion. That itself is the primary valency. So primary valency over here is 3. Okay. How to write the structure? Structure if I have to write, it will be cobalt. Can you like tell me how many solid lines will come and the dotted lines will come for which one to which one? If possible, you try to tell me. Okay. Otherwise, I will be drawing here. So we have 3 ammonia ligands. I'll just write ammonia 1. Yeah, good. So 3 ammonia I have drawn and 3 chloride also I will draw like this. 1, 2 and then 3 randomly. Okay, octahedral geometry. This is octahedral geometry. Okay, now here this is correct because 6 is solid lines we should have because secondary valency is 6. Okay, now like that we should have 3 dash line also, no? And that 3 dash line should be with the chloride ion. 3 dotted lines. Yes, very good. So 3 dotted lines I should draw here with the chloride. That chloride indicates it is satisfying the secondary valencies as well as it is satisfying the primary valency like this. Okay. I hope I made this things clear to everyone. Now I'll give one random question which they ask you in the exam. Okay. The way they ask you the question in the exam. So I will give you that question. You try to answer me that. Okay. So the question is, what is the secondary valency? Okay, you have to tell me what is the secondary valency and the primary valency. Okay, what is the secondary valency and the primary valency? Okay, of the complex. I will give you that complex. Of the complex, this is a complex CO, Cl3, 4, NH3. This is the complex. Okay. So you have to find what is the secondary valency, what is the primary valency of this complex. Okay. In which 1 mole of AgCl is precipitated out. 1 mole of AgCl precipitate they have got when it was treated with AgNO3. So this is the question. So I want you all to tell me what is the primary and the secondary valency for this question. If you want, I will repeat the question once again. You can write down during that time. What is the secondary and the primary valency of the complex? Complex is this, okay? That is COCl3 4NH3, in which 1 mole of AgCl is precipitated. I'll write PPT here, okay? 1 mole of AgCl is precipitated when it was reacted with the AgNO3. When it was reacted with or treated with AgNO3. So you have to tell me what is the secondary and the primary valency in this case, students. Think little bit and give me the answer. Yes, very good. So primary valency over here and the secondary valencies are only the one who are usually answering, only they are answering. What about others? Okay, can you tell me how will be the complex drawn? How will be that complex looking like? Yes, very good. The answers are correct. Okay. The one who has answered me, no, it's correct. The secondary valencies as well as the primary valency answers are correct. I will tell later, but can you all tell me how will be that complex? Like just give me that structure, like how many cobalt, how many chloride and how many iron. If you just give me the number is fine. Yes, correct. Very good. Yes, correct. So this is how it is. Yes, students, correct. Your answers are correct. Okay. So I will give you now here. The question was you have to find primary and the secondary valency. Complex given to you is this, okay? And they are saying 1 mole of AgCl is precipitated out. That means 1 Cl has gone out, okay? That is present outside the complex. So I will put them outside the complex here. That 1 Cl I will put it outside, okay? Because from here AgCl has 1 mole of AgCl has got precipitated out. That means 1 Cl from the complex is present outside. Remaining everything you put them inside, okay? So inside means first always the metal should come, okay? Then I will write the ammonia ligand. We are writing them according to the order, okay? You know how like molecule usually then the order. So I am writing amine first. So NH3, 4 are present inside only, and then from here, since 1 chloride has gone out, remaining will be 2 chloride. Okay. So this will be the particular structure of the complex. Okay. CONH3, 4, Cl2. So from this, we understand that the cobalt secondary valencies, total number of ions and the molecules which are directly attached to the metal, okay, it is 6. So secondary valency is 6. And primary valencies you can calculate, no, that is the oxidation state. So cobalt you can see ammonia is 0, 2 chloride and 1 chloride is outside. So that is a total valency satisfied for the cobalt. So it is 3. Okay. So if I have to draw the structure and give you, cobalt is here and then we have NH3, NH3, NH3 and then NH3. Okay. 3 and then I have 2 chloride. 1 chloride is present outside. Okay. 1 chloride I will just draw out with the dash line because only 1 is here. Okay. And then remaining 2 chloride ion itself is satisfying the valencies because altogether it is 3, no? So 1 is outside. That means 2 more has to come. So those 2 more are from this chloride. Negative ion you have to see. Okay. So they will be having a dotted line. Yes, very good. Correct. 1 dotted line representing the counter ion and 2 dotted lines for the ions which are present attached to the cobalt. Okay. Yes, this much would be enough for you to understand about the werners postulate, as well as what type of questions they will ask you will be this kind only. Okay. Okay, now I'll just have a quick revision of whatever I've done till now. Okay, I'll revise it quickly, and then a small topic is remaining that I'll be doing in the afternoon. Okay, so I'll just revise, students, whatever you have learned so far. So Werner's I will not do. I hope it's clear to everyone about Werner's postulate. So I'm starting from the beginning. Okay, that few definitions we started like that only, no? So in a brief way, I will just do the revision. So from the beginning, what you have learned is this coordination compounds which are there. In that, you will find there is a metal which is present inside. Okay. So you find there is a metal which is present inside. Okay. So this metal is also called as central metal atom. I will label them. It is also called as central metal atom. It can be an atom, or in some cases we have seen they are even ions. Okay, so these are the two of negative or the neutral molecules will be attached. Okay, and they are named as ligands. So to this metal is the one which will be present in the center, so they are named as central metal atom. And to this you will find that there are negative ions, or I said there are neutral molecules which will be attached found to the metal. Okay, they will, yes. So ligands are the one which donate electron to them. So they will donate the electron pair to bind with the metal. So you can label them. L is the ligand. So ligands are the one which donates the electron pair. Okay, it can be one or more than one pair of electron which they will donate so that they can bind with the metal atom. Okay, such type of species are called as ligands. Okay, so ligands can be of different types. You have seen there are ligands which are negatively charged, there are ligands which are neutral, and there are ligands positively charged. Okay, certain kinds of ligand. Negative ligands are like the halogens, you can remember. Okay, I'll just write X minus. Neutral molecules use water, ammonia we have. Okay, and then En, that is ethane 1, 2 diamine, and so on, then NO plus. Okay. Yes, ammonia will be neutral ligand. Okay. So these are the different kinds of ligand. In that also, based on the number of electrons which they donate, in that, based on that, we have types. So there are types of ligand based on the number of lone pair of electrons which are donated by them. Suppose if they are giving only one electron pair, okay, if they donate only one electron pair, then such type of ligands are called as monodentate ligand. They are able to donate only one electron pair, then they are called as monodentate. If they donate two electron pairs, okay, if they donate two electron pairs, they are called as or didentate ligand. Okay, so yes, bidentate ligand because they are able to donate two electron pair. Example, okay, let me give you the example also. For monodentate ligand, the example is NH3, one electron pair, H2O, one electron pair. They can donate, okay. All the halogens will come in this category. Yes, you can write denticity. Denticity is the number of ligating groups present to the ligand, okay. So here the denticity is 1. Denticity means the number of ligands which are directly attached to the metals. Okay, so in this case it is 1. So you can even write that. Correct. Okay. Here in the bidentate case the denticity is 2 because they are able to donate 2 electron pair. Example for that. Can you all tell me what are the examples I have given you for bidentate ligands? Yes, very good. En is one example then. One more was there, no? Oxalate. Yes, very good. So En, that is ethane. It's a abbreviation which we use. Ethane. Okay, this is one. And then we have OX, that is oxalate ion. Okay, it's not oxalic acid, oxalate ion. We write like this, CO minus and then COO minus. So these are the charge which they can donate. Okay. In ethane 1,2 diamine, you have nitrogen which has the lone pair of electron which will be available for donation. Okay. Then we have polydentate ligand. If they can donate many lone pair of electrons, okay, many lone pair of electrons to the central metal atom. Okay, if many electron pairs can be donated, many electron pairs, if they can donate, then we call them as polydentate, then it is called as polydentate ligand. An example for polydentate I've given is EDTA. Okay, that is ethylene diamine tetraacetate ion. Okay, so if you see in this particular structure, you will see that there are two nitrogen, which I will not write the structure because you have already written it. So two nitrogen is there which can donate, and then you will find in that acetate ion, okay, you will find four acetate ion because tetraacetate, no? So there are four oxygen atoms in this acetate ion which can donate. So altogether they can donate around 6 electron pairs. Okay. So they are also named as hexadentate ligand. Okay. These are hexadentate ligand. So it is 6. Okay. Is 6. Okay, so those are the types of the ligand based on how many electron pairs they can give. Then I even told you about the chelating ligand. Chelating are the one which form a ring-like structures. Okay, and in that one particular ligand, there are two donating groups present. For example, this can be a chelating ligand. That is bidentate ligands are there, no? En, I'll just put a star mark here. En is a chelating, oxalate is a chelating, and then EDTA is also a chelating ligand. Okay, these three which I have put as a star mark, these are chelating, means the one which can form ring-like structures. Okay, they can bind with the two donating groups. So they will close that whole structure. Like for example, if I have cobalt here and if En is linking, it will donate 2 electron pair. No? So like this, it will be bounded to the cobalt. Okay. If I take one more En, it will be like this. So they will form this ring-like structure. You can see a ring is being formed here. And this will be more stable also. Then there is another category of ligand which can donate from both the side. Okay, a ligand which can donate from both the side, and such type of ligands are named as, yes, very good, ambidentate ligand. Okay, so they are called as ambidentate ligands. Example for ambidentate ligand, these ligand at a time they can donate from only one side. Okay, yes, very good. So you have thiocyanate and isothiocyanate. So SCN can be donated, and from they can donate from both sides. Okay, that is, they can donate from sulfur side, they can donate from the nitrogen side. So if I take metal here, donation is happening from sulfur, that will be thiocyanate. Okay, but if the donation happens from the nitrogen side, we write it like this. Okay, then this is called isothiocyanate. Even cyanide, very good. Cyanide groups are there which can donate metal, or nitrogen can donate to the metal. Okay, and then even nitro group, as you all said, NO2. So here nitrogen, NO2 group is also ambidentate ligand. So at a time here nitrogen is donating, oxygens are not involved, or if the oxygen is involved, then we write this. Okay, so this is the denotation which we use, indicates that now oxygen is donating. Okay? Both are nitro group. But if it is donating from the nitrogen group, then we write it as nitrito N, and here we write it as nitrito O. Okay, so that's the difference. When you label them, be careful. So ambidentate are the one which can have more than one donor site. Okay, but at a time they will donate, I said, only from one site. Then I told you about ordination number, and I hope you remember about this. Just now, even for the werners, I explained to you. In both the case, carbon is a central atom. In SCN and NCS, Okay, carbon will be in the center and the sulfur and nitrogen will be linked. Yes, correct. Yes, now coming to this coordination number and coordination sphere. Coordination sphere means when you write a metal, okay, when we write a metal, so when you put in a square bracket, these are called as coordination sphere, okay. And the one which are present outside, these are called as counters. So if you take a metal atom and the ligand attached to it, put them in a square bracket, okay, then such spheres are called as coordination sphere. It is called as coordination sphere. It is even named as coordination entity, okay. Coordination entity is one more name given to it. Now inside the ligand which is attached to the metal, they will have different geometry. Okay. The distribution of the ligands will be different. Like they can be octahedral, they can be tetrahedral, they can be trigonal bipyramidal, they can be square pyramidal. So that depends on how many ligands they are attached with. That's very different. And secondary, always the secondary valencies decide the geometry, okay, not the counter ions. Counter ions are just present like a sphere over there, okay, just balancing the charge of the metal. And how many ligands are attached to the metal, that itself is called as coordination number. So it is the number of ligands, donor atom, which is attached directly to the metal inside this sphere, okay. Always check inside the sphere, okay. This again I gave you the example, but let me this. In this case, you can see that the platinum atom is attached to 4 chloride ligand. So here the coordination number will be 4. Okay. The negative ions or the neutral molecules or in general the ligands which are directly attached to the metal inside the sphere. See them inside the sphere. So this is called as coordination number. Okay. The neighboring atoms to the metal. So coordination number is 4. You study coordination number even in the solid state. But in the solid state, what we say is the number of ions which they are directly attached to, the neighboring atoms. No. So here also it is like that only. But the central atom is present here as platinum. Metal is there. And to which they are like the ligands are directly attached. That will become the coordination number. Okay. And then oxidation state. Oxidation state is a charge which the metal carries. So how to calculate the oxidation state for this complex is, I gave you few charges. I told you for halogens, all the halogens minus 1 charge. Chloride, chloride, iodide, everything will carry minus 1 charge. Okay. And if you have OH minus, OH will carry minus 1 charge. And if you have water and ammonia, and then En, all these molecules, they don't carry any charge, they will be neutral. Okay, 0 will be the charge on them. So this at least basic things you need to keep in mind so that you will be able to do the calculation of the oxidation state of the metal. So here platinum I am taking as X because we don't know what is the oxidation state. We can calculate now. Chloride is 4. So minus 1 into 4 because oxidation state of chloride is minus 1. So minus 1 into 4 will be minus 4. Whole charge is there. On the complex, the whole charge is equal to minus 2. So I will write minus 2 here. So what will be the oxidation state of minus 2 plus 4, no? So X is equal to plus 2. Yes, plus 2 will be the oxidation state, correct. Okay. So this is how you calculate. And then there are complexes based on type of the ligand they are attached with. Those are called as homoleptic and heteroleptic complexes. Homoleptic complex means if the, like for example here, this platinum is there, no? Platinum Cl4, it's a homoleptic complex. Why it's a homoleptic complex? Because the ion which is attached to the metal is of same category. Okay. But if I take now here something else, if I take platinum and then HP, then if I write Cl2, in this case what happens? Ligand which are attached to the metal atoms are different. So then these are named as heteroleptic complex. These are heteroleptic complex. because the ligand attached to the metal is different, and it's a homoleptic complex. Okay, homoleptic complex. Okay, because the ligands which are attached to the metal atom is of same category.